Students, in last two lectures of wave optics, we studied different topics which relate to the interference of the two light waves or two or more than two light waves. Now in today's lecture, we'll try to learn condition for steady and clear interference. In previous lecture, we studied the theory of interference band, means when the point is dark and bright in interference pattern. But here in this topic, we will try to learn how the interference pattern clear and steady. Some conditions are there. First condition, the two sources of light should be coherent. How the coherent sources are obtained from a single source of light we learn in Young's double slit experiment. Okay, the two sources of light must be emitting light waves of equal frequency and which are always in same phase, or the constant phase difference are known as the coherent sources. We know that if the two sources are originated from the single source of light, the waves emitted from the sources are equal in amplitude, period, frequency, even they are in the same phase. If the phase difference is same or constant phase difference is there between the waves which is emitted the from the two different sources which are originated from the single source, then the waves will be in phase. Such sources are known as coherent sources. As we learn in the Young's double slit experiment, the two sources should be derived from the same original source. Waves emitted from the two virtual sources will be in the same phase or a constant phase difference, as I said just now. This condition must be satisfied to obtain steady interference pattern. If the sources are not coherent sources, two different sources are used, or the waves from the two different sources which are not originated from the single source of light, then the waves which is emitted from the sources are not in the phase and the interference pattern will not be obtained on the screen. Then second condition is the sources of light must be monochromatic. In 11th science, we learn uh, monochromatic source and polychromatic source. Monochromatic source, the source which emit the light waves of same wavelength. Monochromatic source of the light is the source which emit the light waves only one wavelength, and polychromatic source, the wavelength is not same. When light sources are not monochromatic, polychromatic source hai, तो the source will be emit wavelength more than one wavelength. Different waves with different wavelength will be there if the source is polychromatic source of light. There may be the constructive interference at one point and due to one wavelength, and destructive interference at the same point due to another wavelength. If the wavelength is different of the waves which is emitted from the sources, then at the same point the constructive interference and destructive interference pattern will be produced, and interference pattern will not be clear. So the sources must be monochromatic. Then third condition, the two sources of light must be emit the light waves of equal amplitude or intensity. The amplitude of the waves which is emitted from the two sources must be equal. If the amplitudes are equal, the intensity at dark fringes, destructive interference is zero. Otherwise, if the amplitude of the waves are not equal, the dark is not complete dark, and the contrast will not be there in interference pattern. So this condition is important. If the dark is complete dark, then we'll observe the interference pattern clearly. Next condition is the separation between two light sources should be very small. The two sources uh, and the distance between them, it should be very small. If the sources are sufficiently close to each other, then the interference fringe will be widely separated. Uh, just in previous lecture, we learned the uh, fringe width. Fringe width is inversely proportional to the distance between two sources. That is, x is equal to lambda capital D by small d. Lambda is the wavelength, capital D is the distance between source and the screen, and small d is the distance between two coherent sources. If this distance is small, then the fringe width is in inverse proportion, means it is widely separate on the screen. Next is the sources must be narrow. If the sources are broad, the waves starting from the different points on the source travel different distances. See, path difference should be same. The waves which is emitted from the two different sources which are originated from the single source of light, the path difference is same, then constructive interference will be produced. If the width of the sources is large, if it is not narrow, then different uh, wavelength which are emitted from the source, the path difference will not be same, and such waves when reaches to the screen, the wave will be interfere with another, and their own difference pattern will be obtained. The resultant difference interference pattern is not clear and distinct. This is a very important uh, condition. Sources must be narrow. Then the distance of the screen from the two sources should be large, means capital D. In practice we are using it is 80 to 100 centimeter, that is distance between the slit and uh, the screen. If the screen is quite far from the uh, sources, then the fringe width should be appreciable and widely spaced fringes are obtained. That is, the width of the fringe which is there in the interference pattern will be separate, and clear interference pattern will be obtained at a particular distance from the slit. if the screen is adjusted. Next condition is the two interfering waves must be in the same state of polarization. The waves uh, should be in the state of polarization which is emitted from the two different sources. The two interfering waves must be travel in the same direction. Okay, these are the two more conditions to obtain the clear and steady interference pattern. Then methods for obtaining the coherent sources. Already we discussed Young's double slit experiment to obtain the two coherent sources from uh, a single source of light. A single source a pinhole and light is allowed from a single uh, pinhole. Then this light is allowed to fall on the cardboard which are having two different pinholes, and the light waves from these two different pinholes, as we consider the two different source from the single source of light. Okay, so the light waves which are these kind of sources will be definitely in the same phase or a constant phase difference, hence it is a coherent sources. Here in our syllabus, two more ways are there to obtain the two coherent sources. One is Lloyd's mirror and the diagram is real source. Uh, the light waves from the real source will allow to fall on a mirror. Okay, uh, we'll discuss it. In Lloyd's mirror, the light from the source are made to fall at a particular angle on a plane mirror. A grazing angle is here. This light rays are shown with blue lines in the diagram. Uh, Lloyd's mirror, a source is there, and in a particular angle, the light rays are on the mirror and it reflected back. The reflected light waves with the red light and this reflected light waves gives us a virtual image of the real source, and the light waves from a real source and virtual source will interfere and gives us the interference pattern which is shown over here. So this is about the light waves, the waves which is from the source at a particular angle. If it is falls on the mirror, the reflected uh, rays gives us a virtual image of the real source, and uh, the light waves from this real source and virtual source interfere and will get the interference pattern. So this is the simple method, Lloyd's mirror. One more method is there, that is Fresnel's biprism, and the diagram for Fresnel's biprism is uh, light is allowed to pass through the slit and it falls on the Fresnel's biprism, and after refraction we'll get the interference fringes. Here the biprism consists two identical thin prisms. We studied thin prisms in 11th science whose refracting angle is very small, that is 1 degree, up to 1 degree. Okay, the bases of these thin prisms are joined together and biprism is made. Here in the diagram, ABC is a biprism and the edge of the biprism is exactly parallel to the slit. Definitely the slit is the cylindrical source of the light, and the light which is from the slit exactly incident on the edge of uh, the biprism. Uh, from the two different halos, the light is refracted and interfere with each other. The interference pattern will be produced. If these lines which are falling on the two halos of the biprism, it refracted. If the same lines are produced in backward, we'll get the two coherent sources. S1 and S2 are the two virtual image of the source, that is S slit, and we'll get the two virtual images of this slit S1 and S2. The waves which is from these two sources are interfere and we'll get the interference pattern. So this is the another method to obtain the coherence sources. Now the light waves which is from the two coherent sources interfere and we'll get the interference pattern. Then optical path, the phase of the light waves having angular frequency omega and the wave vector traveling in a vacuum uh, along the x direction. Here kx minus omega t is the phase. K is the wave vector, x is the distance traveled by the wave, even you can say path difference. Omega is the angular frequency and t is the time for which the wave travels. Now wave vector is angular frequency divided by speed of the waves. We know that c is the speed of the wave in the vacuum. So if the light waves travels the distance delta x, then phase difference is delta phi is equal to k delta x, and we know that k is omega by v. Therefore our equation is omega delta x. Value of k is here, that is omega by v. It becomes omega delta x by v. If the wave travels in vacuum, then the velocity is, instead of v, we'll write c. Then equation for the phase difference is delta phi is equal to k delta x. Delta x is the path difference. Formula for the phase difference is equal to k, that is constant wave vector, uh, and it is path difference. This wave vector is 2 pi by lambda, the value we already studied in oscillations. So when light travels in vacuum, will the equation is omega delta x by c. Now wave is traveling in a medium of refractive index n and wave vector is k dash. Now the medium is changed, refractive index is n and wave vector is k. So we'll write k dash is equal to omega by v, but v is c by n. We know that n is equal to c by v. Already we studied this result in the 11th science. N is the refractive index when light is passes from air medium to another medium. Air medium velocity is c and the another medium velocity is v. So refractive index is n is equal to c by v. Here v is replaced by c by n. Okay, therefore the equation for k dash is omega divided by c divided by n. If the wave travels the distance delta x in this medium, then phase difference is delta phi dash is equal to k dash delta x. So we'll write wn n to the numerator and value of k dash wn by c and into delta x. So for this n delta x, the path traveled by the wave in the medium will write with n delta x, and this is replaced by delta x dash. So the equation is omega delta x dash by c. Here delta x dash is replaced by n delta x here. Okay, so the wave travels a distance delta x through the medium and the refractive index is n. The phase is changes by some amount, and it would be if the wave had traveled a distance uh, n delta x in vacuum, we can say that the path length of delta x in the medium of refractive index n is equivalent to the path of the length n delta x in vacuum. So n delta x is the optical path traveled by the waves. If the path is traveled n is equal to 1, then uh, distance speed here n is 1, then distance is common formula, we already studied it. Time is equal to distance by speed. Then t is equal to distance in the medium and the speed or velocity of the wave in that medium. This is equal to distance traveled by the wave in vacuum and uh, the speed of the wave in vacuum. If uh, the light passes through the vacuum, that is frequency of the air medium is n is equal to n, then only we'll write this. Then the an equation optical path means the path traveled by the light waves in the vacuum. So this to this side, that is V in vacuum and divided by V in medium. Again this is C by V and into distance traveled by the wave in that medium will get the optical path. So definitely this C by V is N, already we studied over here, into distance traveled by the wave in medium will give us the optical path. So this is about the optical path. If the refractive index is n, then this is nd minus d, so equal to d into bracket n minus 1. This is the distance traveled by the light wave in the vacuum. So this is about the optical path. Now the next topic in this chapter is the diffraction of light diagram. Uh, and we know that when light travels in a straight line produces a shadow if an obstacle is placed in its path. Here in diagram source of the light, and definitely the light waves which is emitted from the source will be fall on the screen. AB is the slit now in the path of the light waves which is emitted from the source S. Definitely the light waves will be passes through the slit and it falls on the screen, means this is illuminated region, means light should be in this region, but the light bends at the sharp edge of the obstacle and enters in the geometrical shadow. This is the shadow. Okay, this should be the completely dark, but the light waves bends at the corner of the slit and enters in the geometrical shadow. This bending of the light at the corners of the sharp edges of the obstacle is known as the diffraction of light. Bending of the light near the edge of an obstacle or the slit and spreading into the region of geometrical shadow is known as diffraction. Okay, so this is the simple concept we can elaborate by using the diagram. It is very simple. Now, example for the diffraction pattern is when the sun is seen through a fine piece of cloth, we'll see the colored spectra and the luminous border that surround the profile of a mountain just before the sunrise behind it. Sometimes the sunrise is there and a mountain will see some spectra. This is because of the diffraction of light. Okay. Now the this diffraction phenomenon is studied by the different scientists, but in our syllabus, uh, two different scientists and their diffraction phenomena are compared. So first is the Fraunhofer's diffraction. In this, the source of the light and the screen on which the diffraction pattern is obtained is effectively at finite distance. Okay, and from the diffraction system, plane wavefront has to be considered in this case. And diffraction pattern is obtained by using the convex lens. Actually, here screen and the source are at a infinite distance, and the lens is used to get the diffraction pattern. Another diffraction pattern is the Fresnel's diffraction, and the source and screen is kept at a finite distance. Here is the infinite distance, and this should be the finite distance. Lens is not required to obtain the diffraction pattern, and cylindrical and spherical wavefront is considered in this type of diffraction. And in Fraunhofer's diffraction, a plane wavefront has to be considered. Only the same word is here. This should be infinite, this should be finite, because screen and the source is at infinite distance, and the diffraction pattern is obtained by using the lens between screen and the source. So these are the two types of the diffraction. Then Fraunhofer's diffraction due to single slit, and the diagram is uh, the light waves, monochromatic light waves, which is allowed to pass through the slit. Slit is A, B, center of the slit is C, and light is passes through the slit. It allowed to pass through the converging lens, and diffraction pattern is produces. Okay, so this is the very simple explanation, just I explain it. Parallel beam of monochromatic light is allowed to pass through the slit whose wavelength is lambda. Okay, AB is the slit and width of the slit is small a. Okay, and the light waves will allow to pass through the convex lens. It converge and the diffraction pattern is obtained on the screen. Okay, now how is the central maxima produced? You just keep your diagram in the mind. Once again, AB is the slit, A is the width of the slit, center is C, and light waves allowed to pass through the slit. It uh, passes through the uh, converging lens and will get the refraction pattern. Then uh, for the first straight line, light will be fall on the lens, and after passing through the lens, the waves will be reaches to the uh, P naught, P0. These waves travel the equal distance. Therefore, the path difference is 0 at this point, and the central bright or central maxima is produces in the diffraction pattern. The waves which is emitted from the source of the light allowed to pass through the slit, and after passing through this lens, it converges at point P naught. The central maxima is here because the light waves after passing through the lens travels the distance, equal distance. So the path difference is 0 and central maxima will be produces. Then point P in the diffraction pattern is maxima or minima. It depends on the path of the waves which is from the uh, uh, this converging lens. So this point P is maxima or minima. It depends on the path difference. So we'll discuss the path difference. How there is the central maxima is produces, that uh, I'll discuss just now. Then uh, position of secondary minima means at point P, if the minima is there, then what conditions are required to get the minima. Okay, here the waves now, the light waves after passes through the slit diffract, and it makes an angle theta little bit inclined to the straight line uh, light waves which is incident on the lens. Okay, it is shown in the diagram, and little bit diverge by an angle theta, and it passes through the lens, and it reaches to the point P. Point P is maximum or minimum intensity. It depends on the path difference, that is PE. It is shown in the diagram. Okay, so path difference from the triangle ABE is sine theta is equal to BE by AB. So BE is equal to AB sine theta, and AB is the width of the slit. Therefore, path difference will write A sine theta. If the path difference is equal to lambda, the P will be point of minimum intensity, and that is AC and CB. The path difference is, uh, now the slit is separated in two different parts. C is the center of the slit. AC and CB are the two different equal parts of the slit, and the waves which is from these two different parts reaches to the point P. If the path difference is lambda, the waves which is reaches to the point, uh, the waves are integral multiple of n, then minima will be produces at the point. Okay, uh, lambda by 2 is the path, and when it is reaches the path difference is uh, lambda by 2 or integral multiple of uh, lambda, then we'll get the minimum intensity. Okay. Secondary waves from the corresponding point lower half the path is lambda by 2, the minimum intensity will be produces at point P. In general, we'll write a sine uh, theta, that is for nth uh, minima, is equal to n lambda, and n is equal to 1 2 3 is there, then the path difference is sine theta is equal to a lambda. Okay, for nth minima we'll get the minima in the diffraction pattern. Okay, once again the conclusion is very simple. C is the center of the slit, and slit is separated into two different equal parts. The waves which is emitted from the these two halos and path difference is integral multiple of lambda, then we'll get minima. Then maxima, if the waves which is emitted from the two halos is lambda by 2, okay, then the maxima will be produces. So maxima condition is 2n plus 1 lambda by 2. In our new book it is 2a sine theta plus minus n plus half lambda. Okay, if 2 is outside the bracket, 2 cancels, and this becomes n plus 1 by 2. The same equations are there, no need to worry about it, and we'll get the path difference with this equation, that is n lambda. N is equal to plus 1 2 3. We'll get the maxima, or plus minus 1 2 3 means on either side of central maxima we'll get a secondary maxima and minima with decrease in amplitude. So this is about the diffraction pattern we'll get after passing through the slit. Diffraction pattern due to single slit consists of central bright maxima at P naught and alternate secondary maxima and minima on the both side, just I said now. Then width of central maxima. Okay, if the lens uh, Fraunhofer's single slit diagram has to be considered over here. Lens and the slit is very close to each other. Okay, so the capital D, that is distance between the slit and the screen, it becomes equal to focal length of the lens. There is the modification in the diagram. What modification is there? The lens and the slit is close to each other. Distance from the slit to the screen is capital D. If the lens is close, then image will be produced at the focal point. So our distance becomes f is equal to d. Okay, this is the only change here in the diagram. Then theta is small. We'll write sine theta as theta and x by f, that is central maxima and first minima. Central maxima and first minima. This distance is x, and the distance from the lens to the screen is focal length f. So we'll write x by d because f is equal to d. This is equation 1. Then x is the distance between the central maxima and first minima. uh, okay. Then uh, for first secondary minima, n is equal to 1, so lambda by e, sin theta is equal to lambda by e. This is equation 2. Now this equation and this equation is the same, therefore we'll write uh, x by d is equal to lambda by a. This and this, actually this is sin theta from the diagram. When lens is close to the slit, x is the distance between central maxima and first minima. Okay, and d is the distance between lens and the screen, so it is focal length f. Even you can replace f with d. So our equation is sine of theta, or theta is equal to x by f is equal to x by d. Now for first secondary minima, we know that uh, sine theta is equal to n lambda by a, and n is equal to 1 for first secondary minima. Therefore equation is sine theta is equal to lambda by a. Comparing to these two equations, we'll get x by d is equal to lambda by a. Okay, therefore x, that is width of the, no, half part of the width is x is equal to lambda d by a. A is the width of the slit, and central maxima, the width of central maxima is double to this x, so we'll get uh, width 2 lambda d by a, or you can say 2 lambda f by a. D can replace with f. Now picture of the central maxima. Here we said what, the central maxima and the secondary minima and maxima is on either side of the central maxima is this. First minima is at lambda by a, n is equal to 1. Okay, now n is equal to 2, 3. For every integral multiple of lambda, we'll get the minima. And when uh, it divide by 2, here we'll get the maxima. Maxima is 2n plus 1 lambda by 2. At this we'll get the maximum. Here width of central maxima is this distance, and it is 2 lambda d by a. For this equation, which one? Here we have to consider this distance. Central maxima is at p0 and the first minima is here, so this distance is x. This distance is x, so x is determined over here, and if we multiply to this by 2, we'll get this total distance. That's what the width of central maxima is, 2 lambda d by a. So this is about the some topics which is included in the diffraction. uh, so we'll stop here. In next lecture we'll go with uh, Brewster's law and scattering due to polarization. We'll end this topic. Okay, so we'll stop here. Thank you.